a fast forward through all the chapters. I flag what I think is important. If you have questions on anything, please don't hold back. Just let's have this interactive, like a discourse. Whatever you want to have explained once again, let me know. I think it makes sense to kind of see the more global overview again. So we did in chapter 1, we talked about the different branches and tasks of statistics. We talked about descriptive statistics and inferential statistics. Descriptive statistics basically organizes, summarizes, and aggregates numerical information. Inferential statistics uses then these data to basically make estimates and study dynamics that is then being extrapolated to a population. The third task of statistics is also the planning and design of research and analytic approaches, which is not listed here. Some textbooks do list it, and it is definitely also a task of statistics. So basically, you need to look at data and research with analytic classes to understand how data needs to be collected, how does it need to be analyzed, how many data points you need, what frequency, what sample size. So this definitely is part of statistics as well. So understand the definitions. Understand that the population is a defined group of constituents, of members of the group. That's a population, and the sample is a subset of that group, a subset of a population, which basically is then being studied to extrapolate the dynamics of that sample to the greater population and to draw comparisons within that sample. You derive basically different types of variables, and please know those for those quizzes. That's quite a low-hanging fruit of points. You have discrete variables and you have continuous variables. Discrete variables are basically variables that only can take on predefined values to distinguish nominal and ordinal variables. Nominal variables are basically names, like we have, for example, the example of countries for the volcanoes. These are basically nominal variables, and you then have ordinal variables where basically some rank and order is involved in the variable per se. Then you have continuous variables. In distinction to those, you have variables that can take on a full range of predefined values. So you have a predefined range of values, and they distinguish interval and ratio variables, where ratio variables is basically like an interval variable, but it has a meaningful zero and it can't get negative. We talked about the Stroop test. We quantified data here. You basically have category, and here's again a characterization of nominal, ordinal, interval, and ratio. Good example, which I find actually quite a good example how to characterize these four types of variables. So with nominal, you have the name of the cookies. With ordinal, you have the ranking of your favorite cookies. You have the intervals, you have the temperature that can also be zero and can also get negative if you freeze them. And with ratio, you have how many cookies are left in the jar, where zero essentially is a meaningful number, which can't get lower than that. If you're quantifying the observations, then you have here the variables. That's important to understand because you will definitely benefit from knowing how to distinguish dependent, independent, and confounding variables. If you have a question given, a research question given in a short text question, for example, and you ask what's the dependent variable, you need to find that variable that is basically the quote-unquote outcome. Whereas the independent variable is the modifiable, manipulatable variable. Let's think, for example, of the example that we looked at was, we did a scatter plot of athletic performance as a function of exercise put into practicing a certain sport. So your athletic performance will become better the more you practice a sport. That means athletic performance is a dependent variable. The modifiable variable is the independent variable, which is the hours you put into practicing the sport. The confounding variable here would be what is the athletic status of that individual subject that basically started exercising that sport. If that was already a person that was more athletic, that basically will confound your insight in that relationship between exercise and athletic performance. So know how to distinguish these three variables. That's quite important. Then know what measures, and measures are likely referring to the dependent variable. Know that a measure should be reliable and valid. When you think of height, for example, you measure height and you measure it quite accurately with a measuring tape or whatsoever. So that should be considerably accurate. So that makes it a valid measure. If you measure the height of a student on Monday, it should be the same height on a Wednesday. That means it's a reliable measure. There are tests that are not as reliable and not as valid, and that's, for example, we discussed the Rorschach ink blood test in that context, which is not a psychologist, I can't really speak to that, but that's kind of a rather debatable test. Hypothesis testing in the same context is essentially drawing a conclusion based on data that you have at hand, following a certain research question to make a binary decision. Yes or no. So when we have a null hypothesis, as we had for hypothesis testing, is the sample mean identically to the population mean? That's our research question. So we've drawn 100 blood pressure and we want to compare it to the population mean that we know. We are quantifying that sample mean and we're comparing it under the null hypothesis that sample mean and population mean are identical, and we're testing this. If our p-value is smaller than 5%, which is our acceptable alpha level, we're rejecting the null hypothesis and we're accepting the alternative hypothesis. So we made a decision on a binary level. We're rejecting the null hypothesis, yes. Versus we embrace and we accept the null hypothesis as a no, it's not significant. So you dichotomize your conclusion. Important in the context of variables, and this will also be something that you see in many of the questions, you need to have an operational definition. What is a dependent variable? What is an independent variable? What is a confounding variable? And this is essentially nicely outlined here. So if somebody tells you, I have a pet, and I think pet owners are just the happiest people on the planet, and I think that's true for the entire population. So now you have a dependent variable, which is level of happiness, and your independent variable is pet ownership. So you could hypothetically bring this statement to the test by operationalizing level of happiness as the dependent variable and pet ownership as the independent variable. What's a confounder? I don't know. Daily yoga practice. I don't know. SSRIs, like a medication. What else? Exercising. Everything that affects happiness, right? So they are confounders, dependent variables, independent variables, and confounders. That's operationalization of variables and data points. You distinguish in the broader concept, you distinguish between comparative research and correlational research. Comparative research is basically where you compare pet owners versus non-pet owners against each other in terms of the level of happiness. That's comparative. Then you also have correlation analysis. Correlational studies basically mean to find association between two or more variables. Athletic performance versus exercise, hours of exercise in a particular sport. Here, health behavior versus use of a wellness program basically shows a linear relationship. So that's correlational studies. To study various research questions, you basically have different types of research design. In very broad strokes, you have retrospective research and prospective research. Retrospective means looking back. So you have data that was collected for whatever purpose. A lot of my research, for example, in epidemiology, is a retrospective research. We have data collected routinely in dialysis clinics, and we're looking back and we're trying to describe dynamics in the population. Retrospective research. Prospective research is, I think I have this intervention that really will change the dynamic in the population, and I want to study this. And you place an intervention on a certain subgroup of your population, and you compare them to the other subgroup that didn't get your intervention. What's the problem with that? Confounding. Because if you, for example, you want to have people in a certain group. So you have your employees that get access to a wellness program. And then you have another group of employees that do not have access to a wellness program. And your dependent variables, your health behaviors. You basically, if you let those subjects self-select into each group, you will have those with a higher level of health behavior a priori before you even started the study, more likely participate in your wellness program. Then the health behavior at baseline will basically act as a confounder. For that very reason, you randomly assign individuals to either group. By that, you equilibrate and you balance the health behavior of both groups, and you become a suitable comparator that you're comparing your intervention group to. So this is where you take confounding out of the equation. So self-selection into group is a typical case of a confounder. So this will lead to selection bias and will lead to confounding in your between groups design. Again, also important for the quizzes. These are questions that you will be facing. What's the difference between groups design and within groups design? Between group is exactly that. So you have two different groups. You have one dependent variable. You compare the dependent variable at the end of the day between both groups. Logically, right? It's kind of self-explanatory. Within groups, you're basically studying them in March, and then you study them in the same group again in August, and you compare March versus August, where each subject serves as his or her own control, and you look for association in these changes. That's within groups design.
Between group design.
Between group design is, for example, when you look for health behavior after they've been enrolled in that health program for 6 months, and you compare them to employees that were at the very same time not enrolled in that health program. So you compare both groups against each other.
Oh,
between groups, exactly. Exactly. So that's within one group. Typically for within groups design are correlational studies, where you study basically changes and you find for example, you would compare within a group. You compare whether assembly time of a kitchen unit associates with age. That's a within group design. So you basically have like a subset of a population, and you cross-sectionally look at the assembly times and you find associations within that group. Then we briefly talked about data ethics. So that basically is principles that are related to working with data and research at all different levels that involves the design of studies that are basically ethically responsible, that are sound in terms of methodology, data collection that is appropriate for the purpose, respecting the privacy of the individual, statistical analysis that are sound, basically preventing the community from having to suffer through false or erroneous insights, interpretation of analysis that are really correct, and the reporting of outcomes in a way that is A, transparent, B, honest, and C, possible to replicate moving forward. Open science in this context is a rather newer tendency, but it's a very important tendency, basically to make your research very transparent, be very clear what you wanted to do before you started that research, what you have done. That involves even the publishing of codes that you have used to analyze your data, and that even goes as far as publishing the data per se. So many journals, for example, will actually require you to submit your data for your research to the journal that comes in a repository and is basically accessible for the interested reader. You will basically find a lot of examples where you can download actual data sets to replicate those findings. Of note, sometimes you find quite interesting mistakes in there, and authors are not necessarily responsive to that. I had a statistics class when I did my master's, where we basically found like some errors in data sets. It's quite amusing. Okay, data-related problems with research are replication failures. where you basically somebody tries to replicate your research findings, is not able to replicate them. That's a problem. It's usually a design issue, sample size issues, so various problems can arise from that. Problems with data collections, sometimes frequency or inaccurate measures, lab failures, various reasons, and old-fashioned statistics that do not follow state-of-the-art methodology. In terms of data ethics, also keep in mind pre-registration. Before you do prospective research, you need to register your research and you need to clearly define your intervention. You need to define what you want to do, how you want to analyze it, and how you're planning to study your primary outcome, your secondary outcome. So you're very transparent about your conduct. And you need to follow this in the following. And this is to prevent harking, which is hypothesizing after research results are known, which is highly unethical, where you basically you chop your data until you find a significant difference, which is very frowned upon for good reason. So that was chapter 1, important chapter, quite a general overview of what actually is relevant in the context of statistics and research design in principle. That led us then to a simpler and shorter chapter, which was then the first look at data, where we looked into frequency distribution. So this is the example. I did start recording, right? Did I start recording? Yeah. Good. Thank you. So we basically, with frequency distribution, we practiced some first ways to aggregate data in a more digestible format. So basically, we did that by computing frequency tables, grouped frequency tables, and frequency histograms, which is the graphic depiction of data distribution. With frequency distribution, we're taking raw scores and we're basically measuring the occurrence of each individual entry or each individual value, which you have done ad nauseam for the homework. So I think you have a clear idea what that is all about. A frequency table is a visual tabular depiction of that data. A grouped frequency table is basically a grouping of these frequency entries. It's basically just making it less granular, giving better overview. We did the volcano example. Please make sure to understand the principle of it, but I think that was fairly easy. The histogram is basically a way to visually depict this data and to visually look at the data and the distribution over the entire range of available data. You can again decrease the granularity and also depict the grouped frequency tables. This essentially leads then to a shape of a distribution, which the most often discussed distribution is the normal distribution. And this returns quite in a few. But also make sure that you understand the skewed distribution, understand what skewed distribution means, and how to basically, so that's the normal distribution, and how to basically label these skewed distributions. So make sure you don't mix up that the direction in which the tail is pointing is basically referred to in the direction of the skewness. So if you have a positive skew, you have a right skew, or positive skew, then the tail points towards the right, or you have a left skew, then the tail points towards the left. There's a negative skew. The special examples here given is the flow effect and the ceiling effect, where you have a certain threshold above which there are no more entries. Classical example is in a really easy test. Everybody should be coming up to 100, and the majority of students should be somewhere close to that 100, which I hope to see next week. Then we have the flooring effect, which basically the same principle, was a very difficult test that nobody really aces and everybody's to the left. That I don't want to see. Good. Then we have dot plots, which is rather a rarity. I think I've seen like 5 or 6 papers with a dot plot in it. So it's more of a graphical depiction of each individual entry. Only suited for small sample sizes. Good, so that was frequency distribution. That was simple and short. And then we talked next about visual display of data. That should be an easier one. So definitely make sure that you know the different types of graphs we have discussed. So there is a good chance you will have a graph in front of you that you're asked to interpret, asked to label, or asked to give some form of a statement about that graph. So you basically you have positive, negative uses. We talked about the misleading graphs. We talked about the different lies, bias scale lies, sneaky sample lie, interpolation, extrapolation. Know the difference between inter and extrapolation, inaccurate values lie. These are all the examples we discussed. So the common types of graph, and there's really the scatter plot. You all have done it for the homework. The scatter plot is probably the most often used graph in the realm of statistics. You basically, it's a very elegant way to depict data because you have each individual entry, each individual data point as a function of your dependent variable, and the dependent variable is a function of your independent variable. And that's the one I mentioned before. Dependent variable is always on the y-axis, is always on the ordinate, whereas the independent variable is always on the abscissa, on the x-axis. Just keep that in mind. You have in scatter plots linear and nonlinear relationships, which basically would be shown by if you fit here a least square line of best fits through that, and it shows you a linear trend when not too much deviations is happening at the extremes. You're basically looking at a linear relationship. If there's a clear increase, for example, here at the higher levels, this is a typically nonlinear. In that particular way, I depicted an exponential function. How would be a nonlinear relationship? So it's basically, it's more of a visual, at this point in time, it's more of a visual interpretation. Linear, nonlinear, line graphs, scatter plots are not line graphs. So if you have a scatter plot and you're depicting things as a scatter plot, the only line you put in a scatter plot is the line of best fit, which can be fitted using the least square approach or the maximum likelihood approach. Never ever connect all these dots with each other on a scatter plot. That's a big no-no. Where you connect the dots is a line graph, because there you would basically have a situation like that where you basically have a time series. So a so-called time series plot or time plot basically shows you an dependent variable as a function of time. There you can connect the points because you're following the same sample over time. For a scatter plot, each data point is an individual entry. So that's an individual participant in your study. Here, each individual contributes different points at each time. So these are all the same people, hypothetically. Then we have bar graphs and Pareto charts. Easy bar graphs, nominal variable as the independent variable, continuous variable as the dependent variable. One way to depict this, if you ordering these if you order these bars as per their magnitude, you get a decreasing or increasing trend depending on which direction you order it. Then it becomes a Pareto chart. Bar graphs highlight differences, but they can also be used to deceive by basically having discontinued axes. Always make sure you understand this. So it's not well visible here, but basically it's a discontinued axis. Always make sure that you understand all aspects of the graph because it can be misleading. Pictorial graphs, this is just other rubbish. Then we have pie charts, not a big fan, don't use pie charts. And if somebody presents data to you in a pie chart, protest. It's just not a good way to depict data. So basically we have here an overview, and I'm flagging this. That's a good overview. If you have one scale variable and you want to show the distribution, the occurrence of each individual values, show them as a histogram or a frequency polygon. If you have one scale independent variable and one scale dependent variable, this is typically a scatter plot, or if the independent variable is a time series, use a line graph. Yes?
What's the frequency called?
So if you have on a histogram, you fit a mathematical function over the distribution. You remember those typical depictions of the normal distribution? That's a frequency polygon. So it's basically, it takes the distribution of each individual value, it fits a mathematical function depicting this distribution, and depicts it then as one nonlinear line showing the distribution. That's a frequency polygon. Okay, bar graph Pareto chart are one nominal or ordinal independent variable and one scale dependent variable, where you have the mean. Usually it's a mean or a median that is shown on the y-axis, which is the upper end of the bar, or the lower end, depending which direction it points. Then we have two or more nominal or ordinal independent variables, and one interval dependent variable is again a bar graph. Or to read the graph. Know in principle how to interpret these graphs. Always make sure you understand the variables that are in that graph. Yeah, don't use chart chunks, no more array vibrations, grid or ducts. Know how to label them, know where they are. There are definitely a couple of questions in there asking you about chart chunk. Know which one is which one. Multivariable graphs, bubble graphs. You've all seen Hans Rosling talk about his epidemiological data. So these are just up and coming. It's much easier nowadays to create really very powerful graphs with a lot of information contained. Just make sure that you understand all dimensions of that graph. Bar graphs have a huge issue. They basically do not show the individual data points. There are ways around that. So you would, for example, would lose in a bar graph, you would lose all these information, all these individual entries, which is disadvantageous. For that reason, you have advanced ways of depicting data. This is a violin plot. Violin plot contains actually a graph that I like very much in the middle. So the violin plot per se is not a bad graph. I kind of like it. That can be a little confusing because it's a lot of different things going on there. But basically what you have in the inside here, that's a box whisker plot. Box whisker plot basically have a box and they have whiskers. The box basically contains 50% of your middle data. So you have down here, the lower end of the box is Q1. The upper end of your box is Q3. So between Q1 and Q3, you have 50% of your data because it's 25th to 75th percentile. In between, the white dot here, that's the median. That demarcates 50%, the lower 50% of the data and the upper 50% of the data, as you know. So then you have the whiskers. The whiskers basically indicate the Q1 minus 1.5 times the interquartile range, whereas the upper whisker indicates Q3 plus 1.5 times the upper the interquartile range. So that basically in its totality contains 95% of all the scores in your data in a normal distribution. So that's the violin plot, and that's the end of this chapter. Any questions on visual displays? No? So that's chapter 4. And now again, the chapter 4. So chapter 4 is basically the central tendency chapter. So that's like very easy. That's almost not necessary to repeat, but let's just quickly stroll through it. So we're basically having central tendency and variability as the most important markers of a distribution. So we have central tendency, we have mean, median, and mode. Know the difference between all those three. So mean is basically the arithmetic sum divided by the sample size, demarcated, and know the difference between a statistic and a parameter. So that's the tricky questions on some of these questions. A statistic is from a sample. It's indicated as M or X bar, versus a parameter as a population parameter is either indicated as mu. Understand what a median is, that it splits the data in half. So that may actually be something which you may have to calculate or find in some of the questions, that could be something where you would need Excel, hypothetically. So you can use a calculator, you can use Excel, that's fine. But so only one browser window open, which is essentially the quiz.
I can't have a calculator on my computer.
You can have a calculator in your computer. You can have calculator on your computer. You can have Excel on your computer. No Googling. You can have the slides open. You can have your notes open, but no Google exercises, no messaging, and these kind of things. Okay, calculating the median. Hypothetically, you may get the data series, and the question is find the median. That's a possibility. So simple calculations will definitely be necessary to be mastered. So calculation of set scores, calculation of confidence intervals, hypothesis testing, all these things can happen to you. Calculating of the modes, understand the difference of the modes. You have unimodal, bimodal, multimodal distributions. You have, understand the power of an outlier. Know which marker of central tendency is strongly affected by an outlier. That's like a trick question that sometimes gives also some issues. So the mean will always react to an outlier, always, has to, arithmetically has to, because the count doesn't change, but the numerical value changes. So as soon as you include or replace one with an outlier, you still have the same count, but you basically have arithmetically, you have a different sum. So it has to react. Whereas the median is not going to move. Neither does the mode. Actually, if you include new data into a data series, and it's quite extreme outliers. So the first thing that moves always is the mean. The median only if there's a larger number of outliers, then the median starts moving at one point. The mode moves at the very last. Mean, median, mode, range, variance, standard deviation, easy, right? Range is min minus max, max minus min. Interquartile range is first to third quartile, 25th to 75th percentile, middle 50%. Median marks 50% below and 50% above. Then we have the variance, is basically the average squared deviations. The square root of the variance is essentially the standard deviation. Know the difference again between statistics and parameter, population parameter. So you have sigma versus SD or S. And it's basically calculated as the deviations squared summed up to the sum of squares divided by the n and the square root. So that's central tendency and variability. That's an easy one. Come on. Then we have 5. Yeah, sampling and probability. That's actually, it's a shorter one, but it's quite important to keep in mind. Understand the difference between a random sample and a convenience sample. Understand why a convenience sample is the most commonly found sample essentially in research, because it's readily accessible. Random sample is just very hard to practically really accomplish, because it's just randomness is very hard to create. Random samples are almost never used because convenience samples are readily accessible. It's like if you want somebody to fill out a survey and you want 100 surveys to be filled out, you need something that really easily gets you these surveys filled. So the problem with convenience sample is that it is the enemy of generalizability. So know the difference between generalizability or external validity. External validity is a synonym of generalizability. External validity basically is, can this insight of my sample be extrapolated to the population? How much does my sample represent the population? So that's external validity. Yes.
Isn't that always the case? Like, can't you always say it's going to apply to the population if using the correct sample?
Yeah, if you do random sampling, yes, but the problem is the random sampling, right? So if you have a convenient sample because you, I don't know, you wanted to study 100 people from the population of New York City, and you basically you're standing on Park Avenue and you're trying to get a survey of 100 people, this may not be representative of New York City. So that's why generalizability would be exactly that. So if you study generalizability, you basically use estimates from different random sampling points and you compare them amongst each other, and they're differing quite substantially. Those you may remember that I made this point that all the blood pressure studies, all the studies of all kinds of medication are basically studied in samples that are not representative of the Medicare population that are essentially getting these medications. And that's the problem. It's like, to some extent, yes, you can extrapolate the dynamic in the population that you're studying, but do you know for certain? No, you don't. And that's really the problem. And this is external validity. So is that insight that I have from a sample actually extrapolatable to the population? Which is a distinction to internal validity. So internal validity would be, for example, do I have in a randomized controlled trial balance between both groups, or are there basically confounding variables in there? That would be an indicator of a lack of internal validity if there's a disbalance. So external and internal validity. Sure. Generalizability can be improved with replication. So this is when you take your survey and then you go to the different boroughs and you do the same survey there, and then you basically get a more random representation or more generalizable insight into what your survey actually shows. Volunteer samples are obviously self-selected samples which suffer again in terms of generalizability, can be crowdsourcing or MTurk. Talked about this. Same issue with the biased sampling and testimonials are basically not necessarily insightful and to be taken always with caution. Random assignment is essentially done, and we talked about the health behavior. So this is basically this random allocation is done exactly to create these balanced groups that you're studying because you don't want confounding factors in there. Random sampling random sampling or random selection is very hard to use. What you use is stratified sampling, for example. When you see, okay, so my recruitment, I have now a preponderance of non-diabetic patients and I'm lacking the diabetic population, then you would stratify, you would intensify recruitment in a diabetic population, for example. So these kind of approaches do exist. There are also more sophisticated approaches to that. So there's much more to be said about that, but that's just for a first taste of that. Probability, know how to calculate simple probabilities. So you maybe ask some simple questions on that. Don't dig too deep into it, but it's important that you understand what's the probability of a 6 when I roll a die. What's the probability of having 2 6s in a row when I roll it twice, right? Understand these basic principles of probability, and we discussed them, right? Then you have personal biases, confirmation bias, illusionary correlations. So where you basically you have preconceived notions about the dynamic and you find this confirmed, this confirmation bias. Illusionary correlations is like, yeah, I run fast on the marathon when I wear the talisman of my grandmother or something along these lines. So it's basically, it's associations where there are none. Personal probabilities. There is, yeah, subjective probabilities. This is 90% of all statistics are made up on the spot. So this is not something that is to be taken too seriously. This one is important. Expected relative frequency probability. You have trial, outcome, and success. If I draw from a population where the prevalence or the proportion of diabetics is 10%, so let's say New York City, 10% of all New Yorkers are diabetic. If I draw one individual randomly, and I select it randomly from the telephone book, and I draw one individual, I have a 10% probability I'm gonna pick a diabetic. If I draw a sample of 100 people, For each individual, my probability is 10%. That means my sample of 100 people will likely have a prevalence, in case it's generalizable, that is somewhere close to 10%. So 10 out of my 100 people in my sample will have diabetes. Likely not the case because 100 is a small sample. But the larger the sample, the more likely my estimate of the proportion will be close to that proportion in the overall population. Follows the same outline as with the mean of my sample as compared to the mean of the population. The larger my sample, the more likely my mean is going to be identical to the population mean. Same happens with proportions. If I draw 100 different samples of each 100 people, I get 100 different estimates of that proportion. This will basically all gravitate around my true population proportion of 10%. So I can get 7, 8, 12, 11, 9, 13. I get a distribution of these proportion estimates. Believe it or not, this proportion is again normally distributed and can be used for hypothesis testing. We're not doing this in this class, but you may do it in your further statistical education, where you deal with proportion, and hypothesis testing with proportion. Is a process called normal approximation and follows the law of large numbers. So basically you assume that the distribution of your proportion estimates follows a normal distribution, and you can use this then for hypothesis testing, comparing it to a different proportion. And there are formulae that allow you to do that. Independence and probability, yes. So independent estimates of these probabilities are basically being considered independent estimates and mutually exclusive probabilities. Following this outline, and this is rolling the die, having a 6 on a die, it's a success. So you have 1, 6, and you have 1 trial. So you basically have a probability of 1 over 6 because you have 1 out of 6 possibilities. So the probability is 1 over 6. If you do it 2 times, it's 1 over 6 multiplied by 1 over 6. Basically gets you to the probability of a mutually exclusive event. So the probability of having 2 6s in a row is 1 over 6 multiplied by 1 over 6. Confidence is a rating of our confidence that this event will occur, as we have learned most recently with the confidence interval. So this is basically our confidence of the population mean being within our interval. Differential statistics uses now the rules of probability to test hypotheses and to basically test the probability of an hypothesis being true or not true. So basically what the p-value is that we're calculating was calculating the Z score and reading that corresponding p-value is the probability of the null hypothesis to be true. And if this probability is smaller than 5%, we're rejecting the null hypothesis and accepting the alternative hypothesis. So you basically use these rules of probability to make a decision, a binary decision of whether the null hypothesis is true or not. Yeah, here we go. Hypothesis, so the null hypothesis, there's no difference. Research hypothesis, there is a difference. You're basically doing that also by comparison of groups. We talked about control group and experimental group. Experimental group gets the treatment, control group does not get the treatment or get a placebo. Then you have a placebo-controlled trial, right? Making decision, you reject it or you fail to reject. Yeah, we talked about all of this. Yeah, important is type 1 and type 2 error. Type 1 error is when you reject something that you shouldn't have rejected. Type 2 error is when you do not reject what you should have rejected. We talk about this again in chapter 8 in a second. Good. Shocking prevalence of type 1 errors. We talked about this as a result of publication bias that researchers want to publish significant results, and these are most likely to be published in journals. Not sure I would go as far to call them liars, but that's a Norton and Heinzen thing. Yeah, here we go. So that's the cheetah slide, right? Which is going exactly in that. And then we talk next, normal curve, standardization, and the set scores. So the normal curve is unimodal, symmetric, and bell-shaped. It's the foundation of inferential statistics. We'll talk about parametric versus non-parametric tests. The underlying hypothesis or the underlying assumption of parametric test is that there's a normal distribution. So all these tests that we're doing in this class, except for the chi-squared test, is working under the assumption that the underlying distribution is normally distributed. Notably, the distribution of the sample means, not the distribution of the individual scores. So we may still draw samples from a non-normally distributed distribution and still get a normally distributed distribution of the sample means. Only when that is not given, then you need non-parametric tests. But more about that later. That's nothing for now. So the sample, the larger the samples, the more likely it's normally distributed. Standardization is a way to basically characterize the normal distribution curve. You have within one standard deviation, you contain 34% of your population between z equals 0 and z equals 1. Between +1 and -1, you have 68%. Between +2 and -2, you have 95.7%. Between +3 and -3, you have 99%. So that's 99. So that's the 68, 95, 99% rule, which is the empirical rule, the rule of thumb, or the rule by Chepyev. I believe I'm pronouncing this wrong, probably. You can also calculate particular set scores as per the definition of a set score. The set score is the distance of an individual point from the mean, standardized as the number of standard deviation that point is away from that mean. And that can be negative or positive, right? So we'll talk about this. You do this to basically compare apples with oranges. You can also inversely calculate an individual score by multiplying your set score with the standard deviation and add it to the mean. And you may recall this formula because it's the same formula that we're using for the calculation of the confidence intervals. And I do flag this formula because that's definitely something that you will likely be doing on the course. Yeah, apples and oranges, set distribution. You compare things that are not easily comparable because they have a different magnitude numerically, but you basically bring them on a population level, therefore you can compare them with each other. It's done in medicine quite often, for example, with osteoporosis and bone mineral density, or with percentiles, with growth trajectory, and for fetuses or for toddlers. You measure growth of a toddler and you compare them to a population distribution, and to make sure that this individual, this toddler, is really on the right growth trajectory and not fails to thrive. So this is all quite important to keep in mind. So we have here again the characterization: 68, 95.7, 99 sample means, and now we're basically coming from the individual score to the distribution of the sample means. So for hypothesis testing, we need to create the distribution of the sample means. So we have a standard deviation within the population, and we're drawing now a sample. Then we draw another sample. We're drawing 100 samples. We get 100 different means, and these means will distribute in a certain shape or form. And now we assume that that sample I have at hand that I want to compare to my population mean basically has a certain variability. That basically is its marker of precision. And I want to compare the sample mean to the population mean. And I will use this estimate of this variability that basically is a function of the standard deviation in the population and the sample size that I have drawn from that population. I will estimate this variability of these means and utilize this for hypothesis testing in the next chapter. So the obvious association here is, so if you have a wide variability in your population and you draw a sample from the population, and there's a wide probability, and you basically you get a wide spectrum of different values for your sample, so you will have more variability in your sample per definition, right? So also, if you draw then repeated samples, your variability of the sample means is also going to be wider. So that's where the relationship of the standard deviation from the population plays a major role. And then secondly, the sample size. The larger your sample size, the more accurate your estimate of the population mean will be with your sample. So there will be less variability because you're just more accurate in your estimate. As a consequence, there's less variability. Therefore, your standard error of the mean will increase with more variability in your population, higher standard deviation, or with a small n, sorry. With a smaller sample size, your standard error of the mean will also be larger, or smaller with the opposite, right? So that's the idea. That's the so-called central limit theorem. Central limit theorem says that the sample mean is identical to the population mean. You're working under this assumption. And secondly, it's that the distribution of the sample mean is related to the standard deviation of the population and the sample size. So, and then lastly, you can calculate the central limit theorem for a comparison between your sample mean and the population mean by calculating a STAT score. And you're basically building a difference between your sample mean and your population mean. And you're then standardizing this difference utilizing your standard error of the mean. And this is where you're dealing with probabilities rather than individual scores, because you have a certain distribution of those sample means and you're characterizing the probability of that mean and that sample mean being identical. That's where the percentages from a STAT score table are not individual entries of a population anymore, but they are basically probabilities within which you basically see an identical sample mean. And this is where the cheaters come in, and this is where 1.96 is flagged as cheating because it's more prevalent than other measures. Good, so now hypothesis testing. Let's quickly fly over that. Okay, so that's basically super simple, and we've just recently done this, right? So this is relatively fresh in your memory, and there are just a couple of things that are important to discuss again. So we know the standardization, we know how to do all of this. I highly recommend to really also map out that normal distribution and make sure that you indicate what you want to indicate and what you're testing. Because there's this graph, the cholesterol example that I also showed last time, and it makes it more easier that you know against which part of that normal distribution curve you're testing against, because it is possible that they get a one-tailed hypothesis test to do. So just keep in mind that you review these slides. Okay, so we talked about this, yeah, know how to distinguish between above a positive score and at least as extreme as that score. Keep in mind that if you have a STAT score, that p-value is going to be everything to the left. If you want the upper part, it's 1 minus this. That gets you the left over to the right. Make sure that you keep this in mind. Okay, then we have scores, statistics, we have none of that. Yeah, parametric tests, non-parametric tests. Know the assumptions for a parametric test, which is that the dependent variables on the scale measure Participants are randomly selected, which is also an important one, and the population is approximately normal. And know the 6 steps. You may be asked each of these 6 steps. So when we talked about the operationalization of variables, also know how to phrase null and research hypothesis. There's a good probability you're going to get a question like that. Pretty good one, actually. Then determine the characteristics of the comparison distribution, understand the standard error of the mean, standard deviations, understand the confidence intervals, quantify the variability in your sample, determine critical values, comes with the confidence intervals or the cutoffs. So determine an alpha. Are you accepting 5%, 10%, 15%? Make sure that you read the question very carefully and not get caught up in a mistake there. Then basically you calculate the set statistic, which is easy. Difference divided by the standard error. You get to a set score, and then you take the decision whether this exceeds your critical value and you're rejecting or you're accepting the null hypothesis. Significant we know, so this is, we have a null hypothesis and alternative hypothesis where one-tailed versus a two-tailed test. We know that, make a decision. Hierarchy, we talked about hierarchy as hypothesis after research results are known. That's basically you're collecting data, you're working with your data, you're analyzing your data, and then you come up with a couple of cool hypotheses that kind of make sense in your research. That's not how you should do that. You should predefine your research questions and then design and draft your analysis plan following the underlying hypothesis of your research. P-hacking, same problems, quite questionable, because basically then you just start to kind of like look at things like you chop your data down and you basically find subsets that kind of show a significant difference. You shouldn't do that. Ethically and methodologically questionable. And then last, we have the confidence interval. And that is really, that is a rather complicated chapter. I don't know, at least I think it's the more complicated chapter. I hope it's easier for you than I think it may be. So we have with the confidence interval, we have an interval estimate that basically reflects your confidence, the interval within which you're 95% confident that you have your population mean contained. It's an interval estimate, can be a 90% confidence interval, then the critical set that you're dealing with is obviously smaller or larger. 90% confidence interval, is the set score smaller or larger than the one for the sets it's 1.58, so it's smaller. No, 1.65, sorry. It's smaller because you're less confident you're containing your population mean. And it's wider, it's 2.58 for a higher confidence. So 99% confidence interval would be a larger, numerically larger set score. So the calculation is simple. You basically multiply the set score with the standard error of the mean, and you add it or subtract it from the mean, gets you the 95% confidence interval. Calculation, we know this is basically the set score calculated by the difference standardized by the standard error of the mean. Problem with this is, and I cannot emphasize this enough, you get a larger estimate of the standard error of the mean by a larger variability in the population or by a smaller sample size. If your standard error of the mean is larger, your set score is going to be smaller. On the opposite, if your sample size is very low, your standard error of the mean is going to be very small. If your standard error of the mean is very small, your set score is going to be rather large. So you may get a significant difference, although the difference per se is not really large. This is important to keep in mind because you may see a difference that's statistically significant, but clinically absolutely irrelevant. And that's a problem. So therefore, Cohen came up with a effect test that basically allows to take the sample size out of the equation, calculating the difference divided by the standard deviation rather than the standard error of the mean. to quantify the overlap between two populations. Because if you have a larger difference, there will be less overlap. Right? If the difference is larger, the populations are further away, the sample populations are further away, less overlap. Alternatively, if you have a larger sample size, and this is where the sample size comes into play, same difference, smaller sample size, less overlap. So therefore, Cohen's d means to take the sample size out of the equation, put the weight back on the difference, which basically quantifies here the overlap. So calculating the effect size by calculating Cohen's d, which is mean minus mu divided by sigma, gives you Cohen's d, and thereby the conventions allow you to understand the overlap. I'm flagging this. That overlap basically gives you an idea of how relevant your differences are. And these effect sizes can be amalgamated for different studies in one analysis by doing a so-called meta-analysis, where basically you get one aggregated, amalgamated estimate of the effect size across all studies. In the simplest form could be a mean, but in essence, it's a random effects model that basically incorporates the variability of each individual study and allows you to get an overarching effect size estimate. The file drawer analysis means to kind of give you an idea of how solid and how robust this estimate actually is. By quantifying how many hypothetical studies may have had to end up in a file drawer to essentially still create a significant, statistically significant effect size estimate. So this is quite a common estimate provided with meta-analysis. And then lastly, we're talking about statistical power. And the statistical power is the probability that we will avoid a type 2 error. And I'm flagging this table. So for the midterms, it's unforgivable to not know the difference between a type 1 and type 2 error. So if you have no effect and the null hypothesis is true, you have a probability of 100%. If you reject something you shouldn't have rejected, that's a type 1 error. That's a false positive. The rest of, so this is usually alpha. This is 5%, usually, if not stated otherwise in the question. The difference between 100 and alpha is the correct decision. That's the 95% confidence interval. In truth, if there is an effect and the null hypothesis is false, you have a type 2 error where you do not reject what you should have rejected. The correct decision, which is 100% minus the type 2 error, better, is your statistical power. And this is affected by various aspects. So the type 2 error should not exceed 10%. So the power logically should then be 90%. The factors that affect the statistical power is here an increase in the alpha, which is debatable. Secondly, you can make a two-tailed test, a one-tailed test, also debatable. Gets you 5% in one tail. Third strategy is increase of the sample size, or a decrease in the standard deviation. This is possible by studying more participants, right? And this is what you actually need to do when you do a power calculation or power estimation. You're basically estimating how many subjects do I need to study to essentially get a variability that will allow me to reasonably give me a significant result if there should be a significant result. You need, and this is where it's getting really tricky, because you not only need to estimate how many individuals you need to study, you also need to consider how many will actually remain in your study and not quit your study by the end of the time. So you need to keep in mind the so-called attrition rate, which is actually the rate with which you can retain your study participants. So there's a whole list of consideration to be kept in mind. So increasing the difference, and this is obviously the last way how to affect the power. So you basically intensify your intervention, right? So you basically Okay, so I want to see more difference. You want to see more difference between the placebo group and my blood pressure medication group. I just give a higher dose of the blood pressure medication and get the blood pressure down more. Is hypothetically a good idea, sometimes just practically, logistically, physiologically, pathophysiologically, or sometimes also ethically not possible. Therefore, sample size is your easiest way to modify your power and make sure that you get adequate power in your research design. That also answers the last question, is like, why is it important to know this power and to estimate this power? Is because you need to estimate your sample size. Good. Any questions? It's not that much, right? It's like we went through it like an hour, 15 minutes. So that's stroll in the park. You're gonna be fine. Okay, thanks so much. Have a nice evening. Just a second. What's the question?